Good afternoon. This is the final video showing you how to do linear regression. In this presentation, we're going to do a multiple variable linear regression. So for the demonstration, I'm going to give you a different data set. So if you go back to your original data set in Excel, we've basically been working in the data stacked, but now there should be another tab called regression data, and then I've given you a code book, I believe, for regression. If not, I can help you with that quickly in class. This is organized a bit differently and has a different process. So this data was pulled from a chart review and basically was used to try to identify what were the best predictive factors to determine who would likely get better with shoulder rehabilitation. And so as we go across the top, we have 4 different therapists treating. This is the patient's age. These are their initial DASH scores. So a higher number, 70 or 80, means more disability. A lower score means they're less disabled. We also have their visit 5 score and their final discharge score. The total number of visits that they came, and then the visits that they came per week, the change score after 5 visits, and their change score at discharge. We also captured other information at baseline, like their pain level, whether they were male or female, some of their demographic information, and then comorbidities. And comorbidities were limited in this study to basically cancer, alcohol, tobacco, diabetes, and then we just summed up the comorbidity total as just how many total comorbidities did the patient report on their initial intake form. Duration of symptoms in months, and then these are exercises, strengthening exercises that they were prescribed in their first 5 visits. So RROM stands for resistive range of motion. So these are all strengthening exercises. For IR is internal rotation, ER is external rotation, protraction, retraction, and shoulder flexion. So this is the frequency by which the patients were prescribed specific exercises. So we believe that their intervention might help predict their outcome in these patients with shoulder pain. I've removed some of the other measures just to make this a little bit more manageable for you guys in class. So you'll have to import this into SPSS and make sure the data is logical and cleaned. You can insert your codebook regression information into the headings, and then you should have something that basically is going to look very similar to this. Now this is more data, so this is 187 patients, and when we're doing prediction models and regression models, it's really helpful if you want to experiment on a lot of variables or figure out what's going on with a lot of variables. You need many more subjects than you have variables. Okay, so let's go back to the assignment, and then the assignment, basically I asked you, or what I'm going to demonstrate, is that we're going to run a linear regression to determine which factors or which independent or regressor variables or predictive factors, however you want to say it, are most helpful in predicting the change score at visit 5. So for the demonstration, we're just going to try to predict what were the baseline factors that might help us predict how well they change or how much they change in the first 5 visits of physical therapy. So our change score at visit 5 is our dependent variable, and then the other regressor or predictive factors we will consider as the patient's age, their pain level at onset of treatment, comorbidities, duration of symptoms, and initial outcome score. For those of you that haven't taken statistics, you can run regression analysis as enter every variable and see what all of the variables do. You can put them all in and then back out the ones that aren't as meaningful. And then there's a forward regression where you put all the variables in, and then the program will only include those variables that are most significant to trying to predict the outcome variable. So the goal of regression, just like Dr. Capilouto said, is we're trying to predict or explain the variance, and that's where we get into the R-squared values. So we're explaining the variance of all the predictor variables on the dependent variable. So let's do that. All right. So in our SPSS, we're going to go to Analyze Regression, and we're going to do a linear regression. So I was checking, so let me go on and do that back in there. So I'm going to check one thing. For doing a regression, you want to check multicollinearity. So you don't want variables that have high correlations with each other. That sort of is a waste of a predictive factor. So one way to do that is in a linear regression equation, if you put all of the predictor factors into an estimate. So we're going to estimate one of the predictor factors and see how well it is correlated with the other factors. So when you do that, you're basically going to ask it to run a collinearity diagnostic, and no plots are needed for this. We're not going to run any other analyses. This is just the standard default. And so when we do that, we get a variable inflation factor. So we're going to look for that. And the values here are not very collinear. When the variables get up around 3 and 5, then there's likely collinearity. If it's at 10, there's definitely collinearity. All of these factors are at 1. And some statisticians will tell you to keep modifying and changing that, but it's the same procedure, just alternating like comorbidity with age and pain, and run through that. For this example, I'm not going to do all of those. I'm pretty comfortable that these are all relatively independent predictor variables. Excuse me. So we'll go back and actually run our real regression now. So down here in the block of 1, we're going to put all of our predictor variables. Let me make that a little bigger so you can see. So as I said, we're going to have their age, their pain, their initial quick dash score, their symptom duration in months, and the number of comorbidities. And the goal here is to predict their change at visit 5. So what is the best indicator of how well somebody's going to do with early intervention for shoulder pain? So we're going to use the quick dash change score at visit 5. And just to remind you, if you have a 50 at baseline and they go to 20, that should be a 30-point change. That's a good, quite a bit of an improvement after just 5 visits of physical therapy. So I said we were going to do it backwards. So here you can sort of see that you have stepwise, remove, backward, forward. So there's different options. If you just leave it at enter, it just puts them all in, and it doesn't really help you discriminate which ones are the best indicator or predictors of that. So we're going to do a backwards regression. So it's going to put them all in, and then it's going to remove the ones that really don't help explain the variance. Different statisticians, different approaches, depending on the number of variables, you might go about this in a different manner. For your homework, I'm just going to have you do a forward regression just so you can start to see the differences. Okay, so we want it to give us a model fit in our R-squared our descriptives, and our partial correlation. So we want all of these, and then we want our confidence intervals. Typically, as we present that data, we're going to give the parameter estimates, the confidence intervals, and the p-values for the analysis of variance table and for the parameter statistics, which you'll see here in a minute when we run this analysis. I typically don't do a plot. This is where you can make your entry and removal more or less conservative. So this is the standard default, an entry of 0.05, a removal of 0.1. The procedures that I've typically seen in the literature use these as defaults. Your statistician may recommend you to be more or less conservative, but we'll just leave it as the default for this analysis. Okay, so now we hit the button and it runs. Excuse me. Okay, so because I asked for descriptives, it's going to give me the means and standard deviations. Now, if you remember, I said there was 187 people in this study, but we only had 162 that had all of those data points. So that's going to change depending on what you put in. The more data that you put in, the more likely you are to have some missing data. It will only run the analysis when you have enough, when you have something from each of those variables. So if I'd done just a regression equation with one variable, I might have 180 or 187 if I have all the ages. All right, so these are our means and standard deviations of all of our data. So I went on and asked it for correlations, so I already know that the multicollinearity is pretty low, but you can see with this correlation table, looking at quick dash, change score at visit 5s, age, pretty low correlation, initial score was a pretty high correlation, might even be significant if you look at that down here. And it's a 0.00, so that's probably going to be in the model. Duration of symptoms, not so great. Comorbidity was a negative relationship, which would suggest that it might be in the model. So it sort of gives you a first glimpse at what factors might go in the model, and shows you the Pearson's, the significance. Okay. So now the computer is going to tell you there are 3 models that it ran. So the very first model was everything you put into it. The second model, it removed one of the variables. It removed symptom duration, which makes a lot of sense when you look at the correlation of that was basically 0. So it wasn't adding anything to the model to explain what the actual scores visit 5 were. Sort of interesting. Most of the time you tend to think that the longer you've had symptoms, the harder it is to get rid of them, but it didn't seem to be the case for these 162 patients. And then the other the other variable it removed was age. So you're left with some variables in the equation and some variables that have been removed. And what SPSS does is it shows you the analysis of variance and the R squared value, the R and the R squared value for each step. So in the very first step, the R squared value explained 25% of the variance. So 25% of the variance is explained from all the variables we put in the equation. Now, that was significant. That's the significance of change. Okay, so it was significant. But now it's going to remove variables that really don't alter the significance of the model. So the first one it removed was symptom duration.